Hi, today we'll be talking about the alteration of the charge transfer lifetimes in rhenium tricarbonyl complexes. We'll start with an overview of what we'll be talking about. So first, we'll be talking about the versatility of the rhenium tricarbonyls, and we'll be talking about the energy gap law of the phosphorescence shifts. And then we'll be talking about how to choose a stable alpha diamine ligand. And then we'll be talking about the variability of the ancillary ligand relative to the alpha diamine ligand that we have chosen. And then we'll talk about the real world applications that tricarbonyls have. So we'll start with the versatility of the ligand substitution for rhenium tricarbonyl complexes. So why are rhenium transition metals chosen for this type of research? Well, rhenium is chosen because it has low toxicity, it has very long lifetime, and it's well renowned. So all of those are great reasons to choose this transition metal rather than any other transition metal. It's also known that for tricarbonyl additions for rhenium complexes, the pi back bonding that occurs on the rhenium metal is very strong, stronger than any other transition metal that you'll see. So that's also another reason it's chosen other than any other transition metal. Next, for this energy gap law to describe, I don't know if you can see it, hopefully you can, but I'll also upload my presentation so you can see it as well. But for the energy gap law, which is shown here, the MLCT is on the left side and the right says LC, but in our case, we'll just say that that's the ILCT, which is the intra-ligand charge transfer, and MLCT is the metal to ligand charge transfer. So for the alpha diamine ligand, which is shown in blue, which over here is the phenanthroline, that changes the shift of the ILCT. And the more electron donating that ligand is, the redder shifted we see in the energy gap law, which is really good because we want it to be more donating so that the more electron withdrawing a ligand we add, which is the ancillary ligand, that they will coincide with each other so that the gap laws will go equalize to each other. And we want that to happen so that the transition from one to the other are fairly similar, which would be really good for our lifetime, for the photophysics, everything in photophysics that we would see. Okay, so for choosing a stable alpha diamine ligand, here on the left side, you can see the absorbances for some of the ligands that were tried, and you'll see a blue shift and the red shift and this is done with a UV vis. I did not do this one specifically, but I have done this in research. But what this shows you is all of these are phenanthroline substituents, and the one in black is the phenanthroline, the 110 phenanthroline that we want. And the reason that is because if you see the excitation band is lower than the other two, and it is also more blue shifted than the other ones, or excuse me, red shifted than the other ones, which is good. That's what we want. And it is also very low, so that is really good. That's what we want. And it also, on the right side, for the PL lifetimes, you can see with this band right here that it is very, very clean, which is also a really good sign that this is what we want. I do not have the photoluminescence for the other two, but I think this was because they realized that it was so clean and it's all relative that that's what they wanted to use. And so it also, another reasons that we have, which I have listed below, is it gives a really high percent yield, which is really important when you're trying to work up further experiments, because if you have a really low percent yield, you can't keep going with your work. And also is really easily purified, as we can see, and the phosphorescence for the phenanthylline substituent by itself is well renowned. So that's also another reason that we want to. And also, it is so electron donating that the ILCT is exactly where we want it for our range for adding the ancillary ligand. The other ones do not show that at all. They're a little too high. They're too high for the MLCT to interact with it, which is not good at all. So now we can move on to the ancillary ligand substitution that we have been trying to figure out how to do. So on the left side, we can see that if we add the imidazole ligand for the ancillary ligand, we can see that it is blue shifted, which is what we want. The blue, that means that the interaction between the electron donating and the electron withdrawing come close enough to each other that they're equalizing, and then we see that blue shift. Also, on the right hand side, we can compare with the halide chlorine ligand that there is also a blue shift from this, which is really exciting because normally people use the chlorine because it's very stable and it's very easily shown and for phosphorescence properties, which is good, but we want to work from there and try and get the imidazole that we want for our ancillary ligand. And we're shown here that that is possible, which is really exciting too. Now we can also see on this slide from the quantum yield that we do have a low quantum yield, which is also really, really good because that means that we have a very strong electron withdrawing group, which is good because we're also seeing those bands, again, come close in contact, that they're just overlapping with each other, which is exciting, at least for me. Now we can go on to the real world applications with rhenium tricarbonyl complexes. So with what we've learned so far, there are alterations in the ancillary ligand, keeping the alpha diamine ligand constant. So we're not changing that at all. So on the very top left, we'll see solar panels. And rhenium tricarbonyl complexes are in the process of trying to make solar cell complexes that will work. But there's not a whole lot there's not a lot known right now. So there needs to be more research going on with it because the lifetimes that they're getting are not as stable as they would like them to be for solar cells because, frankly, solar panels are expensive and that's not something everyone wants to pay for. So we're trying to get better at that so that it's more affordable for everyone. And to the right, we'll see chemotherapy works, which is exciting to me because cancer is very hard to treat and it's up and coming. So with chemotherapy, we are using rhenium tricarbonyl complexes, yes, you heard me right, to treat ovarian cancers, different strains of it. But with the drug that they're creating, we can see that they are the toxicity of these cells is increasing, and that is shown in this table right here. Yes, it is using a different ancillary ligand, but that's okay because we can change that if we know all of these are phenanthylline, which they are. And so all of the quantum yields that we're getting right here are fairly small, which is really good because we're seeing that electron withdrawing group again meet up with the electron donating of the ILCT and the MLCT, so that's good. And we're also seeing a really long lifetime for this exciton band, which is shown in the third column to the right. And then over to the very far right, which is the exciting part, is the treatment for the cell toxicity for ovarian and the ovarian cistoplatin resistant cell. So if we see in the middle one, the THP, that shows to the right that it has a 30% cell toxicity rate, which is really, really good. I mean, yes, there needs to be more research done on this, but so far that's a good sign to show that these do work in cell toxicity. So for overall, I just want to say thank you for watching this. And I want to thank all of these people who helped me get all of these resources. So NC State Libraries, my PI, Felix, or Phil Castellano, and everyone who really helped me with this presentation and all of these references, all these articles and the internet. So thank you so much for watching. Hope you have a great day.